Hello everyone, welcome to part 2 of the section 8.5 notes. We're just going to pick up where we left off. So for this example we have the sum n equals 0 to infinity, n times quantity x plus 2 to the n divided by 3 to the n plus 1. So first thing we'll do is identify the center of this power series. Notice a in this case, since it needs to be of the form x minus a, I think a is going to be negative 2. That's an important distinction to make, right? Okay, so let's begin with the ratio test to see where this power series is convergent. So you'll notice here we plugged in n plus 1, and for heaven's sakes use parentheses, right? So when you plug in n plus 1 for this n here, you get n plus 1 in parentheses, right? And same here, you'll notice 3 to the n plus 1. When I plug in n plus 1 for n, I get 3 to the n plus 1, right? And again, I'm putting n plus 1 in parentheses. And then I flip and multiply the sum and just as I see it, right? So 3 to the n plus 1 divided by n, x plus 2 to the n. All right, so we're going to stack things that are similar. So I think the n plus 1 is similar to the n. I think this 3 to the n plus 1 is 3 to the n times 3 to the first over 3 to the n. And now you'll notice this is technically a 3 squared, right? Because I get 3 to the n plus 2. And we're going to stack the x plus 2 to the n plus 1, which I'll split up as x plus 2 to the n times x plus 2. And again, I'm using parentheses, right? All right. So now let's cancel some things that are similar. So the x plus 2 to the n is similar. The 3 to the n's are going to cancel. And you'll notice that everything is already positive except for possibly this quantity x plus 2, right? So everything can move out of the absolute values except for possibly the x plus 2. So you'll notice in this limit, the 3 over 3 squared will just cancel to give 1/3. And now verify this to yourself however you like, but n plus 1 over n, as n becomes large, goes to 1. So I get 1 times 1/3 times absolute value x plus 2, which is just 1/3 times absolute value x plus 2. And now if you'll remember, I need to require that this, in order for convergence to hold via the ratio test, I need that to be less than 1. And now I haven't solved for the absolute value, so what this tells me is that x plus 2 is less than 3. And so automatically, once I've done that, I get my radius of convergence is just 3, right? So r equals 3. Okay, so now let's look at our supposed interval here. My center 3 is, my center minus 2 is right here. And now I'm allowed to go 3 units in either direction, right? So at most I can go up to 1, and at least I can go down to minus 5. So let's first plug in minus 5. So I get the sum n equals 0 to infinity, n times minus 5 plus 2, all to the n over 3 to the n plus 1. Well, that's the sum n equals 0 to infinity. I get n times minus 3 to the n over 3 to the n plus 1. And that is, and this plus 1 is in the exponent, of course. And I'm going to simplify this. I can split up minus 3 to the n as minus 1 to the n times 3 to the n. And similarly, this on the bottom can be split up as 3 to the n times 3. And we notice the 3 to the n's canceling. And so this is the sum n equals 0 to infinity of minus 1 to the n times n over 3, if you like. You'll notice this is going to diverge. Not only are these numbers getting arbitrarily large, n over 3 as n becomes large, you'll notice that the limit as n goes to infinity of this sum and doesn't even exist. And so this must diverge by the test for divergence. Okay, so I get an x here. I'm not allowed to use x equals minus 5. All right, let's try x equals 1 then. We get the sum n equals 0 to infinity, n times 1 plus 2 to the n over 3 to the n plus 1. You'll notice this is 3 to the n, and the bottom I'm going to split up also as 3 to the n times 3, and we see the 3 to the n's canceling. And so this is, once again, the sum of something that doesn't even go to 0. Notice the limit as n goes to infinity of n over 3, well, that's infinite, which is definitely not 0. So this diverges by the test for divergence. And so neither the endpoints work. And so my interval of convergence is strictly minus 5 to 1. Okay. Coming down here, go ahead and pause the video if you like. Try this one yourself. First, we're going to identify the center. That's a equals 2. Now, setting up the ratio test, you'll notice I'm going to plug in inside absolute values n plus 1 everywhere I see n, and notice once again I'm using parentheses, and then flip and multiply, just plug it in as I see it, right? The sum n, that is. Okay, so this is the limit, n goes to infinity. We're going to stack similar things, so this is x minus 2 to the n times x minus 2, and don't forget the absolute value bars. And here I get x minus 2 to the n. And here I get n squared plus 1 over n plus 1 all squared plus 1. Once again, the x minus 2 to the n's are going to cancel. Only the x minus 2 could possibly be negative. Since n is large and positive, this whole fraction is always positive. So this is just the limit as n goes to infinity. Absolute value x minus 2 times n squared plus 1 over n plus 1 all squared plus 1. And once again, justify this limit to yourself any way that you like. N squared plus 1 over n plus 1 squared plus 1 is a rational function, and we're going to infinity. The powers are the same, so it's the ratio of the leading coefficients. The limit is 1, and so this is just absolute value x minus 2. And if you remember, I need to require that that is less than 1 via the ratio test. And so have I solved for absolute value x plus or minus a number less than some quantity? Yes, so that tells me that my radius is r equal to 1. Here's my center 2, so I'm allowed to stray 1 unit at most in either direction, so either to 3 or to 1. And now we're just going to check the endpoints. So let's try 1 first. You'll notice that this is minus 1 to the n over n squared plus 1, the sum of that. What do you think? Does this converge or diverge? Well, to me it looks like an alternating series. So I think my bn is going to be 1 over n squared plus 1. Is bn decreasing? Yeah, I think so. And is the limit of bn going to 0? Yes, I think so, right? And so this converges by alternating series test. So I'm going to put a check mark here at 1. Let's try x equals 3. So this is the sum n equals 0 to infinity of 3 minus 2 to the n over n squared plus 1. And you'll notice that this is 1 to the n, and 1 to the n is always 1, right? So this is just the sum n equals 0 to infinity of just 1 over n squared plus 1. And there's a few ways to convince yourself that this converges. I'm going to, just because we haven't seen it in a while, I am going to do the limit comparison test. Notice that this looks like 1 over n squared. And so let me try the limit comparison test. So I take what I have and divide it by what I think it looks like. And as long as that limit comes out to be a finite positive number, then I am good. Well, this limit came out to be 1, which for the limit comparison test is a good thing. Limit comparison says as long as it comes out to be a finite positive number, you're in good shape. So well, let me say here, it converges by limit comparison test since the sum 1 over n squared I know converges. Remember, that's a p-series with p equal to 2. So I get another check mark here at 3, and so my interval of convergence is 1 to 3. All right, so for this last one here, you'll notice I have, if we want to identify the center, it's very, very tempting to say that the center is a equals 1, but look inside this parentheses here. I don't have just x plus or minus a number to the n, right? So let's hold off on finding our center. We'll come back to that a little bit later. But let's set up our ratio test here. This is the limit n goes to infinity. Once again, plug in n plus 1 everywhere you see n. Flip and multiply the sum and plug in just n as you see it, right? Okay, so I get 2x minus 1 to the n times 2x minus 1, put parentheses around everything, divided by, and now we'll stack similar things here. Okay, and now I get a 5 to the n over 5 to the n times 5, I think. And then I get a root n over root n, n plus 1. All that's inside absolute values. The 2x minus 1 to the n's cancel, 5 to the n's cancel. That's a 1/5, right? And this here, well, n is large and positive, so these square roots are positive. So the only thing that needs the absolute value is this 2x minus 1. I got that 1/5. And this limit, if it helps, you can think about this as n over n plus 1 all square rooted. And now when you compute the limit, notice the only thing that depends on n is this expression right here, and the limit can move inside the square root, and so you get the square root of 1, essentially, which is 1 itself. And so this just comes out to be absolute value 2x minus 1 times 1/5. And if you'll remember, I need to set that less than 1, right? Multiply both sides by 5. And so once again, it's tempting to say that my radius of convergence is r equals 5, right? But let me caution you against that. We have not got x plus or minus a number inside this absolute value, right? I haven't quite solved for it yet. You'll notice that I have this 2 here. Well, I can factor that out. So what I'll say is this is like 2 times x minus 1/2 with the absolute value around the x minus 1/2. And you'll notice then that now to solve for absolute value x minus this number, I need to divide by 2. So this says x minus 1/2 is less than 5 over 2. And so my radius is actually now 5/2, r equals 5/2. And so let's look at what the center is. The center is now 1/2, right? And so with my center 1/2, I'm allowed to go 5/2 units in either direction. If I add 5/2, I get over here to 3. And if I subtract 5/2, I'm back here at minus 2. So the first endpoint I'm going to plug in is minus 2. And you'll notice I get, if I plug in x equals minus 2 here, I get minus 4 minus 1 all to the n. Well, that's the sum n equals 1 to infinity of minus 5 to the n over 5 to the n root n, which I can split up as the sum minus 1 to the n times 5 to the n all over 5 to the n root n. And you notice the 5 to the n's cancel. And so this is the sum n equals 1 to infinity minus 1 to the n over root n. What do you think? Does this converge or diverge? Well, it's alternating, so alternating series test is probably the right thing to do. Does Bn decrease? I think so. As n gets larger, these fractions are getting smaller. And is the limit as n goes to infinity of these Bn values equaling 0? Well, yes, right? So this converges by alternating series test. And so I get a check mark by minus 2, okay? Now come over here, plug in x equals 3. Go ahead and try it yourself if you like. You get sum n equals 1 to infinity. You get 6 minus 1 all to the n over 5 to the n root n. Notice this is 5 to the n, which will cancel with the 5 to the n on the denominator. So this is just the sum of 1 over root n. And now this, what do you think, converges or diverges? I think this diverges. It's a p-series with p equal to 1/2, right? And so I get an x above the 3, right? The 3 doesn't work. And so my interval of convergence is minus 2 to 3. See how that works? Okay, and now finally, and this is a neat little example here. Suppose we know that the sum from n equals 0 to infinity of Cn times 4 to the n converges. Can we conclude that the sum of Cn times minus 2 to the n converges, or the sum Cn minus 4 to the n converges? And the answer may surprise you. But before we can answer that, let's remember what the general form of the power series is. So remember, it's always the sum of Cn times x minus a to the n. Okay, so my a value here is the center. And so if when I plug in some x value, I get an output of 4, what must I have plugged in for x? Well, I think that's a plus 4, right? If I plug in a plus 4 for x, then I get Cn times 4 to the n. See that? And I know that I have a check mark here. So what that tells me is I'm allowed to stray at least 4 units away from my center. So what that tells me is that my radius of convergence, my r value, is greater than or equal to 4, right? So what that tells me then is that I know everything within a plus 4 to a minus 4 is golden, right? And so what if I plugged in a minus 2? Well, what would I get if I plugged in a minus 2? I know it's going to work because it's in this radius here. Well, I would get exactly this one, right? If I plug in a minus 2 for x, I would get a minus 2 minus a, which is minus 2 to the n, right? So I get sum of Cn minus 2 to the n. But like r could be, r dead on equal to 4 could be a possibility, in which case it's possible that this left endpoint doesn't work, but the right endpoint does. And we've seen this many times, right? I mean, look at the last one we did. One of the endpoints worked and one of the endpoints didn't, right? So, and I don't know, I don't have enough information. So for this one, I can't conclude anything, right? I can't conclude that it converges. It doesn't automatically follow that it converges. I don't have enough information to conclude that. So this one, the first one, I can definitely say converges, but this one here, because it may well be the other endpoint of my interval of convergence, it may diverge. I can't say for certain. So I like that example. That's a neat one. But that's the end of section 8.5.